Dear all, I'm presenting the course given by Vincent Gage of the University of Toulouse on special metrics in Kahler geometry and Kahler-Ricci flow. But unfortunately, we forgot to record the first two lectures, and then I am redoing the lectures. Actually, the second one was already redone by Eleonora Di Nezza, and I will now redo the first lecture following the notes, the slides of Professor Gage. So let me try to share the screen. Okay. Okay, can you see the screen? I hope so. Then, okay, so let's start. And okay, now we want to explain the notion of Kahler metric on a complex manifold, usually compact, complex in our case. And then we motivate the search of canonical Kahler metrics, which is Kahler metrics on a given manifold defined in a canonical way, so that the existence or non-existence of such metrics is giving us information on the manifold. And then in the second lecture, which was already done by Eleonora, she discussed the notion of quasi-harmonic functions. And so let's start. Okay. X, we take X to be a compact complex manifold of certain dimension n larger than 0. And we look at an Hermitian form on the manifold, which is analogously to the Riemannian geometry, the assignment of a positive definite Hermitian form on each tangent space, complex tangent space to the manifold. Then once you have an Hermitian form, you can take the real part of this form, and this gives you a Riemannian metric on the manifold. And then you can look at minus the imaginary part, and this will give you a two form on the manifold. Or we assume that the Hermitian form varies in a smooth way when you move the point, as in the Riemannian case. And this minus imaginary part is a two form. It's called so it's antisymmetric. This can be extended to the complexified tangent space, C-linearly extended to such space, and then you can write it, say, in local coordinate, local holomorphic coordinate, and this looks like a form like this. Summation of ij goes from 1 to n of omega alpha beta I dz alpha dz beta bar. So it's a 1-1 form. And okay. And we say that the metric is the Hermitian metric is scalar if this two form is closed. That is, if d omega is equal to 0. So okay. for example, the Euclidean metric in any open set of Cn is a Kahler metric. But if you, for example, if you multiply a metric by some function, even non-negative function or even positive function, you destroy the Kahler condition. But another, in the compact case, an example of Kahler manifold is tori. The tori are quotient of Cn modulo some lattice. So so therefore, since the action of the this is the covering map, holomorphic covering map, and the transition function, or I'm sorry, the covering transformations are translations. So the Kahler metric in Cn is invariant, and then you can push down the Kahler metric to the quotient, which is the torus. So the torus is an example of a Kahler, with the flat metric is an example of a Kahler manifold, Kahler metric. Kahler manifold is some manifold which admits at least one Kahler metric. Okay. Now the complex projective space CPN is also Kahler manifold, and the Kahler metric is the so-called Fubini's 2D metric, which is defined locally in the above way. Suppose that you have Z0, Z1 homogeneous coordinate, and you assign Zj to be equal to 1, so that you have charts x1, xn with the 1 at the jth position, and then in this local coordinate you say that the form omega is defined to be I over 2 pi dd bar of log of 1 plus norm of x squared, and these forms, which are a priori only locally defined, they attach, they glue together, and then they define a global Kahler form, and therefore a Kahler metric on the complex projective space. Okay, this is another basic example. Note that if you add to some Kahler form omega IDD bar of some function phi, and you assume that this omega plus IDD bar phi is still, it's certainly still a 1-1 form and it is still closed, but if you assume that it is still positive, so it comes from some positive Hermitian metric, then this will be another example of a Kahler manifold, of a Kahler metric on your manifold. In particular, if the norm, if this the C2 norm of your smooth function phi is sufficiently small, then omega plus IDD bar phi will be also Kahler if omega is Kahler originally. And okay. Another example, simple, is a product of Kahler metric when you have just the sum of the two Kahler forms. Omega xy is omega 1x plus omega 2y. Okay. And also, if you have embedding of some manifold x into some manifold y, and you assume that y is Kahler, then you can pull back the Kahler metric on y, and then you would still, since f is an embedding, you will also get a Kahler form, which will give you a Kahler metric on your manifold x. In particular, this happens when f is an inclusion, so that x is a complex submanifold of y. Okay. In particular, any closed or even any locally closed embedded submanifold projective space is Kahler. And for example, since you can embed any Riemann surface compact Riemann surface in P3, then any compact Riemann surface is a Kahler manifold. Actually, any Riemann surface itself is a Kahler manifold. Now choose, take a ball B in Cn. So this is also a Kahler manifold because it's an open set in Cn. And you do the blow up. What is the blow up? Blow up is the subset of the product B cross P of n minus 1, ZL, such that Z belongs to L. So this becomes a complex submanifold. You can check easily that it is a complex submanifold of the product B cross Pn minus 1. Actually, Pn minus 1 or Pm, sorry. And this actually this is also B tilde is also a Kahler manifold. And note that B tilde is a simple structure because if you can look at the projection from B tilde to Cn on the first factor from B tilde to Cn. So the fiber over the pre-image of any point different from 0 is just 1 point. Actually the pre-image of 0 is the entire projective space Pn minus 1. This pre-image of 0 is called the exceptional divisor. It's usually denoted by E. Okay. And then the projection is then a biolomorphism from B tilde minus E to B minus 0. But so you replace 0 with some projective space in some sense. Observe that omega, since it is a Kahler form, it is closed, then it defines a cohomology class. Okay. And what one can prove is that you can take the push forward by the projection pi of the form DDC of log of norm of z plus norm of z squared. This DDC is just I 2I over pi d bar, and it's a real operator. That's why it's interesting. But the point is that DDC of log z norm of z plus z squared is a Kahler form downstairs on the Cn. But if you take the pullback, then this becomes only semi-positive because it's actually the 0 form restricted to the fiber of 0 to the E. However, you can correct this pi per star to construct a new, an actual Kahler form in your manifold. And this is, say, cohomology. In cohomology, at least, you can find a Kahler form such that on the blow up, such that the cohomology class of this new Kahler form is equal to the cohomology class of pi per star DDC z plus z squared minus the cohomology class of the E in brackets, which is the so-called integration current of E. What is a current? A current is essentially similarly to distribution. What is a distribution? A distribution is a continuous linear function on the space of smooth functions of compact support. Then a current is a continuous linear functional on the space of smooth forms of complementary degree, so that you can take the integral and get actually functional. So the integration current is just acting on, say, some n-1 or actually 2n-2 form with compact support is just the integral over E of this form. Okay. Now, actually, the construction of the blow-up can be made locally in a manifold. That is, you can take a manifold, take a point, take a small neighborhood of the point, holomorphic to a ball, blow up this small neighborhood and reattach this, and then you get the so-called blow up of the manifold at the point. And this is also, again, Kahler. So if the manifold, the original manifold is Kahler, then the blow up is also Kahler. Okay. Then there's also another important characterization of Kahler manifold, which is by local holomorphic charts. And if you may recall that in Riemannian geometry, you can always find near any single point a system of coordinates such that the metric is in this coordinate at the 0 point, say 0 corresponding to P. It's the identity, is the identity matrix, and the derivatives of the matrix of the metric G is the first derivative are all 0. But this is in general not possible for Hermitian, generally Hermitian forms, Hermitian metrics on complex manifold. But metric is Kahler if and only if you can construct a holomorphic local coordinate system such that at 0 you get the identity and 0 first derivative. That is, omega is the identity up to second order. Okay. Essentially, being Kahler means that the metric is compatible with the complex structure. More precisely, you can say that omega is Kahler if and only if the Levi-Civita connection of the real part of the Hermitian metric commutes with the complex structure J. This is another way of characterizing Kahler metrics. The local DD-bar lemma, what is it? It says that any closed 1-1 form can be written locally, has the IDD-bar of some function. And this is a general fact on any, locally is a general fact on any complex manifold, or any actually closed, any closed 1-1 form can be written locally as IDD bar phi, and general fact. But in the case of Kahler metrics, compact Kahler metrics, you have also okay, so let's say then omega is locally IDD bar phi, and the condition that omega is positive means that phi is the so-called strictly inclusive harmonic function. Eleonora will talk about more extensively about inclusive harmonic function in the next lecture. And but in the Kahler world, you have also, in the compact Kahler world, you have also global DD-bar lemma, which means suppose you have two Kahler forms, omega and omega prime, and suppose that they define the same cohomology element, since they are both closed, we said they define cohomology. So suppose that they define the same cohomology, then their difference is IDD bar phi of some global function phi, global smooth function phi. This is true on compact Kahler manifolds. That's the so-called very famous DD-bar lemma. Okay, and therefore, if you fix one Kahler form on a Kahler manifold, you can look at all the function phi such that omega plus IDD bar phi is still a Kahler manifold. That is, omega plus EDD bar phi is what is called a positive form, positive 1-1 form. And this gives you a cone in the space of 1-1 forms, and it indicated as K omega usually. Okay, now another very important fact is the so-called Hodge decomposition theorem. That means that on a complex Kahler manifold, the cohomology of X with value in C is the sum with P plus is isomorphic to the sum with P plus Q equal M over the HPQXC, which is, this is HPQ is this P cohomology of the sheaf of omega Q, big omega Q of X. Big omega Q is the space of holomorphic Q forms on X. Okay, and also you have natural isomorphism between HPQ and HQP, which is defined by the just by conjugation, say on the harmonic forms. So in some sense, so that these two guys, HPQXC and HQPXC bar have so this is not a holomorphic linear map, but it's a anti-holomorphic somehow. Okay. Then, oh, this shows also that first this Hodge decomposition says that the first cohomology, the dimension B1 of the first cohomology H1XC is equal to 2 times H10, which is H10 plus H01. So this is all an even number. And therefore, whenever you have an example of complex manifolds that the first Betti number D1 is not even, then this can certainly not be Kahler manifold. An example is the quotient of C2 modulo the action Z goes to 2Z. And this gives you a compact complex manifold which is not Kahler. Okay. Now, the notion of holomorphic line bundles. Okay, what is a holomorphic line bundle? It is a complex manifold of one dimension more than the original X, such with a projection pi, such that the pi inverse of X is has another structure of a complex vector space of complex dimension 1. So it's somehow isomorphic to C, and that in such a way that you can trivialize the bundle. That means that any point has a neighborhood U such that there is a polymorphism between pi inverse of U and the product U cross C, which we call it phi U, in such a way that phi restricted to X to the pre-image of X is a linear. No, it's so this is some map which will commute with the two projections. So it maps Lx, the pre-image of X, into X cross C, and we want to that this map is a linear isomorphism. Therefore, we require that the change of coordinate phi u, phi v inverse defined on the intersection of u cross v maps the pair x z xi into some x gu v of x xi, where this gu u v of x is invertible. No, it's a complex number. It's a non-zero complex number. So this GUV is actually a map from your intersection U intersection V into C star, into C minus the origin, holomorphic. And okay, and these GUV are called transition functions, and they are non-vanishing holomorphic functions on the intersection. Okay, then you can make some operation on the line bundles. For example, the tensor product, which would correspond to taking the product of the two transition function, the dual, which would correspond to take 1 over the transition function. And okay, the trivial bundle is just the bundle X cross C, which corresponds, you can choose identically 1 as a transition function. Okay. Very good. Now, so the group of all line bundles with this tensor product operation modulo isomorphism of line bundle is called the Picard group of the manifold X. What is a holomorphic section? A holomorphic section is a map from X into L such that pi composed with S is the identity, which means that to any X in X you associate a point in the pi inverse of X, that is in the vector, in the one-dimensional vector space fiber over X of pi. A holomorphic section is a holomorphic map from X to L. And so you can, if you have a trivialization, then you can write a section locally, and this gives you just a holomorphic function. So, but a collection of holomorphic functions for each open set U of your, say you have a trivialization on a covering, then if you change from U to V, the condition that this family of holomorphic section must satisfy to define a global or this, sorry, the condition that this family of functions must satisfy to define a global holomorphic section is this SV is GUV SU. Okay. Now, if you have a base, so the space of sections is certainly a vector space because you can sum two sections and multiply a section by a complex number. And then you can have a basis of sections. It can be proved that the space of sections of a line bundle on a compact complex manifold is always finite dimensional. So you assume you have n sections which form a basis. And then you can look at the for any x, S0 of x, as n of x, they are element in the fiber over x. So it's a product of the fiber n plus 1 times. And since this is a basis, if you assume that H0 has is not identically 0, at least one of these, S0 as n, must be non-zero at x. So you can define homogeneous coordinate S0 as n in brackets and get point in the complex projective space. This defines a map, say, from the manifold X to CPN, which is well, maybe not globally defined, but it's defined at least if X0 is not reduced to 0, it's defined on some open set. And okay, the line bundle is called very ample. This field is globally defined all of X, and it gives an embedding of X into the projective space. Okay, and it's called very ample, and it's called ample if some power of it is very ample. Okay. one basic example is the so-called hyperplane bundle. On CPN, on the complex projective space, and what you do is, usually this guy is called O1. We start from the dual of it, which is called O-1. It's called the tautological or universal bundle on PN. So what is a point in PN? A point in PN is a line in CPN, in Cn plus 1. So you associate to any point Z in Pn its line. So the O minus 1 is the pair of Z Xi, where Xi belongs to Z. So this is the projection on P1 gives you, on Pn gives you exactly the so-called the tautological or universal bundle. The dual of this is defined is denoted by O1, and it's called the hyperplane bundle. Note that O minus 1 has no non-zero global sections. However, O1, the global guy, the dual of O minus 1 has lots of holomorphic sections. In fact, the transition function of O1 can be written as Zi over Zj, where Zi in the region where Z are the homogeneous coordinate and Zi and Zj are both non-zero. And then you see that this guy, local functions define as global section of O1 if and only if they satisfy the condition above, which is if and only if they are they are just a linear degree 1 polynomial in n plus 1 variable. So the space of global sections of O1 is the space of polynomial of degree 1, homogeneous polynomial of degree 1 in Cn plus 1. And so if you tensor O1 a certain number of times, say n times, then you get the global section of this bundle called On is the space of polynomial homogeneous of degree n in the global section of O of j is the space of polynomials of degree j in n plus 1 variable, and they have dimension n plus j over j. Binomial coefficient, and this is like when j goes to infinity, it's like j to the n, and therefore, okay, that's all for the moment for the projective space. On a complex manifold, you have a very important basic line bundle, which is called the canonical line bundle, and it's the line bundle whose global holomorphic sections, if x has dimension n, the global holomorphic sections are the space of n forms of holomorphic n forms. So locally, if Z1, Zn is a holomorphic coordinate, then dz1 wedge dz2 where dzn wedge defines a local nowhere zero n form, holomorphic n form, and the transition function of this non-zero section defines a trivialization of the bundle, and the transition function of this trivialization is just a Jacobian of the coordinate changes, of the holomorphic coordinate changes. And this canonical line bundle is the most important one. In the case of Pn, for example, the canonical bundle of Pn is O minus n minus 1, so it has no sections. No global sections. Another example is the canonical bundle of the hypersurface of degree d is O of d minus n minus 1. So if d is sufficiently large, this canonical bundle has sections and may have a lot of them, according to what is the value of d. Okay, exactly, that's exactly what we want to say, that if d is smaller than n plus 1 or equal or larger than n plus 1. So if it is smaller, there's no sections. If it is equal, there's essentially one-dimensional space of sections. And if it is larger, then there's a lot of sections, a large dimensional space. Okay. Another important example is that observation is that the canonical bundle of the product is just a pullback by the projections of the two canonical bundles. And the canonical bundle of the torus is, since any n-form on the torus can be pulled back to an n-form, holomorphic n-form on Cn, and the dz1 wedge dz2 with dgn is a global nowhere zero holomorphic n-form on Cn. This shows that the canonical bundle of the torus is just is trivial. It's isomorphic to the canonical bundle of the torus is isomorphic to the trivial bundle. Okay. What is the curvature of a holomorphic line bundle, or more precisely, of some Hermitian metric on a holomorphic line bundle? So we want to first say what an Hermitian metric is, and okay. So if you have your function, your section defined by a family of function SU, you want to say what is the norm of SU in your metric, which would just be the norm of the function multiplied by some positive local function. This positive local function is usually written as e to the minus phi u, and the condition for this phi u to define a global Hermitian metric on each on the line bundle, meaning a Hermitian metric and a Hermitian scalar product on each fiber, is that phi v is phi u plus log of the norm of GUV, or GUV is a transition function. And this allows you to find the norm of a section, of a global section in a well-defined way, this condition. Okay. Now, the curvature of the metric is IDD bar phi u, which is equal to IDD bar phi v, because on the intersection, IDD bar of the log of GUV is 0. So these local guys, IDD bar phi u, they glue together to define a global 1-1 form on the space. This global form is called the curvature form of the bundle. Okay. The line bundle is defined to be positive if there exists the metric H on the line bundle is said to be positive if the curvature of H is a positive 1-1 form, so that if it is the Kahler form of some Kahler metric on the manifold. Okay. And the Kodaira embedding theorem says that complex manifold X is projective, that is, can be embedded into some projective space if and only if it exists a line bundle on holomorphic line bundle on X, which admits Hermitian metric, which is positive, which has positive curvature. Okay. Now we want to define another important guy, which is called which is the first Chern class. If you look at the transition function of a line bundle, they satisfy the so-called co-cycle condition, that is GUV times GVU is 1, and GUV, GVW, GWV, WU is 1. Therefore, they defined a cycle on the so-called check cohomology, and this, since these are nowhere zero holomorphic functions, this is the check cohomology of the sheaf of nowhere zero holomorphic functions. So they define as an element in the so-called H1XO star, which can be then identified with the set of holomorphic line bundles modulo isomorphisms, or as we said before, with the Picard group of X. Now you have some exact sequence of sheaf, very important, so-called 0 goes to Z goes to O by the inclusion, goes to O star by the exponential map, and locally this goes to 0. So this is an exact sequence of sheaves, and therefore you have the induced exact cohomology sequence, and then you have a map from H1 of O star and a connecting map, so-called connecting map, goes to H2 of Z. Then if you have a line bundle L, this guy represented by some element in H1 XO star, and you go into H2 XZ, and the image is called the first Chern class of the line bundle. Okay. And it's denoted by C1 of L, and therefore lives in H2XZ. But then you can look at the inclusion of Z into R, and this gives you a map from H2XZ into H2XR. And then you can look at the first Chern class in H2XZ and look at the image in H2XR. And another important fact is that the cohomology class of the image C of L into H2XR is the same cohomology class of the curvature of any Hermitian metric on the line bundle. Very good. The first Chern class of X is by definition the first Chern class of minus the canonical bundle of X. Okay. Now we want to try to classify manifolds, complex manifolds, and then you can look at the global section of some power, tensor power, the canonical bundle of some compact manifold X, and it can be shown that this is always of the form J to some power nu, which is an integer, which might be minus infinity, 0, 1, up to n, the dimension of the manifold. Minus infinity means that this guy's H0, X, K, X, J are all just 0. 0 means that they are essentially one-dimensional. So they grow like 1 at infinity when J goes to infinity. The dimension grows like 1, and and then otherwise they can grow at any integer between 0 and n. If this nu is called the Kodaira dimension of the manifold, and if this guy is n, if the Kodaira dimension is n, and we say that the manifold is general type, okay, and the Kodaira dimension is birational invariant, so two birationally equivalent manifolds have the same Kodaira dimension. The simplest example is the Riemann surface case. Then you have three cases. Kodaira dimension is infinity, that is this minus infinity, which means that there's no sections of any power of kx, and this is the case for x is p1, or any power of kx is trivial, then you have a torus, an elliptic curve, or the rest is that you have a so-called hyperbolic manifold covered by, so the universal cover of them is the unit disk, holomorphic universal covering is the unit disk, and in this case, kx is Kodaira dimension 1, and actually the canonical boundary is positive, so it has Hermitian metric with a strictly positive curvature. The classification in dimension 2 is also almost complete, and it's done by in the school, Italian school of the beginning of the 20th century. And okay. Now we change the argument. Subject, we look at x omega compact Kerr manifold, and we want to define what is a scalar and Ricci curvature of a compact Kerr manifold. The Ricci curvature is expressed locally in this way, always in a holomorphic coordinate system, minus 1 over pi summation over alpha and beta of d square log that g of dz alpha dz beta bar, where g is the expression g alpha beta I dz alpha dz beta bar is the expression, local expression of omega. This guy is this local one form can glue together. Actually, this Ricci is again the extension to the complexified tangent bundle of the Ricci form of the Riemannian metric associated. And the scalar curvature is instead a trace with respect to the metric G or the form omega of the Ricci, which can be written as n times the Ricci wedge, Ricci omega wedge omega n minus 1 divided by omega n. And as we said, this is globally well defined. And moreover, you can see from the global, from the local expression that if you take two Kahler forms, eta and omega, then the Ricci of eta and the Ricci of omega differ by the DDC of something. Therefore, they define a global, the same cohomology class. È successo. They define the same cohomology class, and And therefore, okay, this is important. And actually, this cohomology class is exactly C1 of x, which is minus C1 of kx. Okay, so there's essentially this is the Verschern class. Now we can define what we mean by special Kahler metric. We say that the Kahler metric is Kahler-Einstein if the Ricci of omega is a multiple of omega. Recall that they are both 1-1 forms, so we can ask whether it's possible to find such an omega, such that the Ricci is lambda omega. Then, where lambda is just a constant, then in particular, this gives taking the trace, it implies that the scalar curvature is constant. And so we say that the metric is constant scalar, is a constant scalar. It's a Kahler metric with constant scalar curvature, so-called CSCK, if it has a constant scalar curvature. So clearly, any Kahler-Einstein metric has constant scalar curvature, but the vice versa is definitely not true. However, because the condition for having one Kahler-Einstein metric is certainly cohomological. If you have a Kahler-Einstein metric, then the cohomology of the Ricci omega must be equal to the cohomology of lambda omega. But the cohomology of the Ricci is C1, so you have to require a necessary condition to have a Kahler-Einstein metric is that C1 is lambda times the cohomology class of omega. But actually can be proved that if the C1 of x is lambda times the cohomology of omega, then any constant scalar curvature metric, Kahler metric in the cohomology class of omega is also Kahler-Einstein. So you can reverse in this case once you have this topological condition. Okay. Now, also, since if you take the Ricci of some multiple of omega, then you get the same thing as the Ricci of omega. Then you can rescale the metric and reduce to the case where lambda is either 0, 1, or -1. And these are three quite different cases. Observe that this topological condition that says that the metric is a multiple, the cohomology of the metric is a multiple of C1, it's certainly not always satisfied. For example, if you take the product of two Riemann surfaces, S1 and S2, for example, if you take product of a P1 and hyperbolic surface, then with the ok, un attimo, che è arrivato qui. Aspetta un momento. Aspetta un momento. Allora. Ok. Aspetta, siamo arrivati. Okay, let's just a moment with some technical problem. Also, let me. I'm not sure that this was already done by some technical problems. So let me start again with the notion of Kahler-Einstein metric and scalar curvature metric, and then so we say that metric is Kahler-Einstein, and the Ricci is lambda times omega. Okay, and where we expect that when we require that this lambda is a constant, so in this case the scalar curvature is also constant. But so this means that Kahler-Einstein implies constant scalar curvature, but vice versa might not be true, because if you have a Kahler-Einstein metric, this implies a cohomological condition, which is saying that the cohomology of the Ricci must be the cohomology of lambda omega. But the cohomology of the Ricci is C1 of x. So we must require that C1 of x is lambda times the cohomology of omega. And this condition, if you have this topological condition plus a constant scalar curvature metric in the cohomology of omega, then this will be Kahler-Einstein. However, this okay, first of all, another point is that you can rescale the metric so that the Ricci of a multiple of omega is equal to the Ricci of omega. Then you can rescale the metric and require that lambda is 0, 1, or -1. But you have to observe that this topological condition is not always satisfied. For example, if you take as X a three-dimensional manifold, which is a product of two Riemann surfaces and one as two, like for example, P1 times an hyperbolic Riemann surface, compact Riemann surface, this will not satisfy the topological condition. So this will not have Kahler-Einstein metrics. The construction of the Kahler-Einstein matrix is the main goal of this series of courses by Professor Gage. Examples are the torus with the flat metric is Kahler-Einstein and has Ricci equal to 0. And the Fubini's 2D metric is also Kahler. And if you do the calculation, you can see that omega is this one, delta alpha beta 1 over 1 plus d squared, z minus z alpha z beta bar over 1 minus d squared squared. And therefore, doing the calculation, you see that the that is that, and therefore you see that, maybe I won't stay a bit longer. The logarithm of the determinant is the logarithm of 1 over 1 plus t squared to the n plus 1, which is minus n plus 1 log of 1 plus t squared. Therefore, you see that Ricci of omega is n plus 1 omega. So with lambda positive in the projective case, projective space case. Okay. References: Zhang, Complex Differential Geometry, International Press of Boston, year 2000. Latzesfeld is a more algebraic geometry book, Positivity in Algebraic Geometry 1. Voisin, Hodge Theory and Complex Algebraic Geometry 1. Zachelidi, An Introduction to Extremal Keller Metric, or slightly older one, but always very interesting. The Tian, Gang Tian also has a book on extremal Keller metric. So I guess the first lecture is done, and I will say hello, say bye-bye to everybody. Ok, vediamo che